Hello, welcome to Smart Sessions by Smart Interviews. In this video, we are going to solve a problem called remove nodes from linked list from lead code. You can find the problem link in the description below. I highly recommend you to pause the video over here, open the problem statement, understand it thoroughly and see if you can come up with a solution on your own. Alright, let's get started. The problem says that you are given the head of a linked list. You have to remove every node which has a node strictly greater than the current node's value anywhere to the right side of it, and we have to return the head of the modified linked list. If you look at the first example, the given linked list contains 5 nodes 5, 2, 13, 3 and 8. If you look at the node 5, it has multiple strictly greater nodes on the right side which are 8 and 13. So, 5 should be removed. Similarly, if you look at the node 2, it has multiple greater nodes on the right side which are 13, 3 and 8. So, even 2 should be removed. If you look at the node 13, there is nothing greater on the right of 13. So, 13 should stay. If you look at the node 3, it has 8 on the right side which is bigger than 3. So, 3 should be removed. If you look at the node 8, it has nothing on the right side which is bigger than 8. So, 8 should stay. Hence, the output is 13 and 8. If you look at the second example, for every node, there is no node with strictly greater value on the right side. Hence, all the nodes stay in the final output. Let us try to understand the problem statement better. So, this was the given example. For the node 5, it is being removed because there is at least one node on the right side which is greater than the current node. Same for node 2, same for node 3, node 13 and node 8 will remain in the output. If you look at it in a different way, it is not required to check with all the nodes on the right side. You can simply check the current node with the maximum node on the right side. So, for the node 5, the max on the right side is 13. Since 13 is greater than 5, 5 should be removed. Similarly, for node 2, the max on the right is 13 which is bigger than 2, hence 2 is removed. For node 13, the max on the right is 8 which is smaller than 13, so 13 should stay. For node 3, max on the right is 8, so 3 should be removed. For node 8, max on the right is say 0, so 8 should also stay. Hence, the output contains 13 and 8. If we try to implement this exact logic, for every node we will iterate on the right side, find the max, compare the current node with the max node. If the max is greater than the current node, we will not add the current node to the output. If the max is smaller than the current node, we will add the current node to the output. If you do exactly this, for every node you are iterating on the complete right side. So, it will take n iterations for every node. Since there are n number of nodes, overall iterations becomes n into n which is n square. And for the implementation perspective, we can always start with a empty node, say a dummy node, and we can keep appending the nodes to the current node. Say the node is D. The moment we see that 5 is less than the max on right, we do not consider 5, same thing for 2, but for 13, the moment we see that 13 is greater than the max on the right side, we will add 13 to the new list. We will simply say d dot next equal to 13, d equal to d next. We should move d forward because the next node has to be appended to 13, and we should also make 13 of next as null. So, this piece of code looks something like this: d of next equal to 13, then d equal to d of next, and then at the end we make d of next as null, because even in the new linked list the last node has to point to null, and we do not even know if there will be other nodes here or not. So, it is always better to link the last node to null. So, if we implement in this manner, it is going to take us n square iteration. However, we observe that every time we are iterating on the right side and finding the max. Instead of that, let us see what happens if we reverse the linked list. So, the reverse linked list will look like this. You will have 8, 3, 13, 2 and 5. Now, for a node 13, whatever you are looking on the right side of 13, you are finding the max, right? The max here was 8. Now, instead of looking on the right side, you will be looking for that on the left side. So, it becomes easier for us to just maintain a max variable. Say we initialize max to -1 and we keep iterating on the linked list and we keep updating the max. So, we are starting our iteration from 8. When we compare 8 with -1, that is 8 with max, 8 is bigger than max. That means there is no greater value on the right of 8 in the original linked list. So, 8 should remain. As discussed, we will maintain a dummy node. So, this is the node D. We will simply make d of next as 8. We will move d to d of next and we will make d of next as null. We are simply executing this piece of the code. Before we move to the next node, we will use the current node to update max. So, max becomes 8. Now, we compare 3 to 8. Since 3 is smaller than 8, we should not keep 3. So, 3 should not be appended to the output list. Before we move forward, we will try to use 3 to update max, but max will remain 8. Now, we are at 13. We can see that 13 is bigger than 8. Since 13 is bigger than 8, 13 should stay. So, what we will simply do is, we will again execute the same piece of code. We will append 13 to d. So, d dot next equal to 13, d equal to d of next and d of next equal to null. Again we move forward. Before moving forward, we will again update max with the help of the current node. So, max becomes 13. Since 2 is less than 13, we do not append 2 to the output. We move forward. Since 5 is less than 13, we do not append 5 to the output. We move forward. We reached the end of the linked list, so we stop. If you look at the output, we got 8 and 13, but the expected output is 13 and 8. Since we reversed the linked list at the beginning, we have to also reverse and return the output. So, we should reverse this, which will give us 13 and 8, and we should return that as the output. Of course, the initial node is a dummy node. It should not be considered for returning the output. We should be reversing only this part and returning that part. So, if you look at the modified logic, once we reverse the linked list, it becomes easier for us to simply maintain the max and use that to decide if the current node should be added to the output list or not. Overall, the number of iterations will be firstly n for reversing the linked list, again n where we iterate on the linked list with the help of the max variable and decide if the current node should be added or not added to the output, and again at the end we will reverse it, which will again take n iterations in worst case. So, if you see the overall difference, this was n square, but this became n, which is much better than the first solution. Take a pause over here, try to understand the logic thoroughly and see if you can convert the logic to code on your own. Okay, so let us try to write the code in C++. We are given a function called remove nodes, which accepts the head node of the linked list. As we discussed, the first step will be to reverse the linked list. So, let us say head equal to reverse of head. So, reverse is a function which will help us reverse the entire linked list. Once that is done, we saw that we will simply maintain a max variable, say max is initialized to -1. Also we saw that it will be helpful for us if we use a dummy node. So, let us declare a dummy node, list node d equal to new list node. If you are calling the function with no parameters, it will give us a node with the value as 0 and the next will be initialized to null, which is completely fine, which is good enough for a dummy node. Now, we will simply start iterating on the list while head is not equal to null. If the current node compared to the max is bigger, we will keep it, otherwise we will not keep it. So, if head of value is greater than max, that means there is nothing greater than that on the right side in the original list. So, in that case we will keep it. Keep it means we will append it to the dummy node. So, d of next equal to head and we move d to d of next. We also make d of next as null and will always move head forward. So, it can be outside the if condition, head equal to head of next. If you observe over here, we also need to update the max. So, inside this itself we can update max as head of value. Since the condition says that head of value greater than max, so we can update max as head of value, and at the end we should simply return the reverse of the output linked list. Since we are using a dummy node and we are moving the dummy node forward, we can't use that anymore. We should store the dummy node into a variable, say temp. Also, as we saw, temp, which is a dummy node, is not useful, but temp of next is the one which will help us. We can simply return reverse of temp of next. So, that is it for the main logic. For the reverse function, we can write it in two ways, either an iterative version or a recursive version. For this video, I will be writing a recursive version of the reverse function. We are not going to discuss how to reverse a linked list. If you are not aware of that, I highly recommend that you read about how to reverse a linked list in both iterative and recursive manner. You can write any of those codes over here. Let us go ahead and write the code quickly. So, list node star reverse of head will simply reverse the remaining part of the linked list. So, we will reverse head of next and we will delink it by saying head of next equal to head and head of next as null. Like I said, I am not going to discuss the logic for reversing a linked list, I am simply writing the code in this video. We will return whatever we get from the reverse function at the end, and since it is recursive code, we will also need a base condition. If head is null, or head of next is null, we simply return head from there. That's the code for reversing a linked list in recursive manner. Let me just move this entire code to the public section. Let's try to run the code and see whether it works or not. So if we are running the code, we see that we are getting a wrong answer. For the first test case, the output should be 13 and 8, but we got only 8. For the second test case, all 1 should be there, but we got only one of them. So what went wrong? If you look at this, head of value greater than max. That means current node is greater than the max found so far, but the problem says that you will remove the node only if it has a node with strictly greater value. So that means even if current node's value is equal to the max, we should keep it, we should not remove it. Let's try to run the code now. So again, it's not working. For both test case 1 and test case 2, it's still not working. Maybe there is something else missing as well. If you look at this piece of the code, we are updating max to head of value. We are making d of next as head. We are moving d to d next, and we are making d of next as null. So this d is nothing but the head node, and we are making head of next as null. So when we do that and we are moving head to head dot next, obviously it's null already, so it will not get any more nodes. So we should not do this before doing this. So what we can do is, we can remove this code from here and we can simply keep it at the end. After processing all the nodes, for the last node we can make the next as null. It's not required to do that again and again. Let's try to run the code now and check. So if you see, the code is working fine for both the sample test cases. Let's submit and try. The code worked fine for all the hidden test cases as well. So in this video, I hope you learned the trick that sometimes for problems of a linked list, if you simply reverse the linked list, you can get a better solution. That's the first thing. Second thing, while manipulating the links of a linked list, it's helpful if we start with a dummy node. And thirdly, it may happen that you get a runtime error or you get a wrong answer if you miss some simple conditions in the code. So here we missed two things. First thing was, the problem said that we should compare with strictly greater node. That's the first thing we missed. Second thing, while manipulating the links, we somehow made that node as null, which we needed for the next iteration. So we fixed both the things and the code worked as expected. See you in the next video. Thank you for watching. Please like, share and subscribe for more such content.